Okay, so a few more things about the hypergeometric random variable. The first thing I want to draw your attention to is, again, we're comparing the hypergeometric to the binomial. They have the same expected value, okay? So in terms of the expected number of successes in a sample of n, where the fraction of successes in the population is p, using the hypergeometric lingo there, uh, is not affected by whether you are sampling with replacement or without replacement. And I remember thinking that was weird when I first encountered it. And you might think it's weird too. So let's just convince ourselves that it's really true. Okay, is it really the case that the expected value of this hypergeometric random variable equals NP? I'm not going to do a general proof, but I'm going to show you in the context of an example that I think will be pretty convincing. Okay, so my example is going to be, and the sample is 2, the population is 5, and we're going to assume that there's 3 successes in the population. So that's a kind of a pretty easy population to envision, a pretty small sample. So just kind of thinking about what else we might care about. P is, as always, little m over small n, so the number of successes in the population divided by the population size, and that's 0.6. Okay. So xh here, that's our hypergeometric random variable. That's the number of successes in n trials and draws here, and a sample of 2 without replacement would be the best way to say that. But what I want to do is define another random variable that's not x. Okay, what I want to do is define y here. Y such that y equals 0 if the first draw from the population is a fail, and y equals 1 if the first draw is a success. Okay, so again, we are sampling without replacement. So it means when we draw that first one, we're not putting it back. We're drawing that first marble, we're not putting it back in the urn, or we're sampling that first person, we're not putting them back in the pool there. But we will be drawing another one. Okay, so why is this kind of random variable that's telling us something about the first step towards getting to x? And we kind of know that this is the difference between the binomial and the hypergeometric. If we put that guy back in the population, then the second draw from the binomial is just the same as the first. But the fact that we're not putting it back means that the second draw from the hypergeometric depends on the result of the first one. Okay, so we're going to model out that conditionality here. And y is going to help us do that. So just finishing up our PMF for random variable y, the probabilities of that are, well, the probability that the first draw is a success is just our 0.6, and the probability that it's a failure is 0.4. Okay, fine, that's all good. Here, the reason why I'm defining y is I want to now write down the conditional PMFs for x, depending on y equals 0 and y equals 1. Okay, all right. So the possibilities here overall for x is, in our sample without replacement of n, we could have 0 successes, we could have 1 success, or we could have 2 successes. Okay. So let's just kind of think about the conditional probabilities here. If the first draw here was a fail, what does the sample look like? What's left in the urn? So the first one was a fail. We took out one of the fails. We've still got 1, 2, 3 successes, and we've got 1 fail left. Well, I'm at it, I might as well do the other possibility. If we're in the world where the first marble that we drew, the first person we sampled, whatever it is about that, we counted it as a success. There's only 2 successes left now, and there's 2 fails. Okay, so if my first draw is a fail, the probability that overall both my draws are both fails is just the probability of selecting the one fail out of the remaining set of 4. Okay, so I started with a population of 5. I'm left with 4. If I'm going to get an overall number of zeros, in addition to the fact that my first one was a fail, I have to get this fail again. Okay, so the probability that that happens is 0.25. Okay. Right? It's that probability because now that we've taken one of the population out and we're not replacing them, we've got 4 left. 3 of them are successes, 1 is a fail. So the 1 fail out of the 4 total here. And the probability that overall my sample of 2 has 1 success in it, given that my first one was a fail, is just the probability that in my second draw, I get 1 of these 3 successes, and that happens with probability 0.75. And the possibility of 2 successes when I've already had a fail, that is 0. All right, fine, that's what happens when my first draw that I'm not replacing was a fail. Now what if my first draw that I'm not replacing is a success? Well, now I've got 2 successes left and 2 fails, and right away here, I know that the probability that I'm going to have 0 successes when I've already had a success, that's 0. Fine, that's nice and easy here. And now the probability that I have 1 total success just is the probability that my second draw is one of the 2 fails, 0.5, and the probability that my overall sample has 2 successes in it is just the probability that my second draw is one of the 2 successes. Okay. All right, so I've got my 2 conditional probabilities here, conditional on the first draw being a success. Wait, this was the one, first one, conditional on being a success, conditional on the first one being a failure. In both cases, the probabilities sum to 1. Let's go ahead and calculate the conditional means. Okay, so the, give myself a little bit more space here, the expected value of X. Remember, X is the hypergeometric. It's the total number of successes in my sample of 2. That is just going to be 0 times 0.25 plus 1 times 0.75. That equals 0.75, but I have to remind myself which expected value I'm calculating here. This is the one that is conditional on y equals 0. And because I'm conditioning on y equals 0, that's why I'm using these probabilities. So 0 times 0.25 plus 1 times 0.75 gives me 0.75. Okay, and then over here, the expected value of h conditional on y equals 1 using these probabilities is 1 times 0.5 plus 2 times 0.5 sounds like 1.5. Okay. All right. What can we do to calculate the overall expected value of X? We can use the law of iterated expectation. How cool is that? So let's do it right over here. Let's pick one little corner of the board here using the law of iterated expectations here that tells us the expected value of this random variable, whatever it is just equal to the expected value of that random variable conditional on y equals 0 times the probability of y equals 0 plus the probability of that guy conditional on y equals 1 times the probability that y equals 1. Okay, so all I'm doing is like I always do with the law of iterated expectation, I'm taking the weighted average of the conditional means. Okay, so mean conditional on y equals 0, mean conditional on y equals 1, and the weights are the probabilities of the conditioning events. Plugging in those numbers. So expected value of x conditional y equals 0, that's 0.75 times the probability that we're in the world of y equals 0. Okay, that was 0.4 plus the expected value when y equals 1, 1.5. Calculated that over here, times the probability that y equals 1, that is 0.6. And when we work that out, we get 1.2, which is indeed NP. Okay. So yes, we are getting the answer that we expected. And by working through the law of iterated expectations, I think you can see the reason why the law of iterated expectations always works. Yes, once we have a conditioning event, once we know what the first, the outcome of the first draw is, our probabilities are changing here. But before we know how that first draw is going to go, before we know whether the first marble is going to be a success or a failure, the only information we have is the information about the overall portion of successes in the population and the number of draws that we're taking. Okay, so the fact that the trials are not independent does affect the probabilities of the actual outcomes. And we'll talk in a minute about the fact that it affects the variance, but it does not affect the expected value. Okay, so that's pretty cool. But like I say, there's some things to talk about with the variance as well. So what do we have for the variance here? Again, we're kind of comparing the binomial variance to the hypergeometric variance. And what I would notice here is that the variance of the hypergeometric is, let's make this a little bigger here. It's just this variance of the binomial multiplied by something, okay? Let's just take a note that this thing is this thing right here, okay? So a way of saying that is that the variance of the hypergeometric is this other factor, capital N minus lowercase n divided by capital N minus 1 times the variance of binomial. Okay, fine. This is a number here. The thing to notice about this number is that this is less than 1 whenever n is greater than 1. Okay, whenever n is greater than 1, this is going to be a smaller number. The difference is going to be a smaller number than what's in the denominator. We're subtracting a bigger number whenever n is a bigger number than 1. Kind of belaboring this point here. But those are the cases we care about, right? We're only interested in this when the sample is bigger than 1, then we're back to a Bernoulli trial when it's only equal to 1. So what this is telling us is that in the cases we care about, the binomial variance is bigger than the hypergeometric. Okay, or since we're talking about the hypergeometric, let me say it in that order here. Okay, so the hypergeometric variance is smaller. Okay, and maybe a way to see that I'm going to elaborate on in just a minute is with an example. And what I'm going to show you in the example is that this smaller variance comes from the replacement in the binomial case allows us to repeatedly draw the same outcome, even if it's unrepresentative. Okay, so you can get more extreme outcomes there. So let's just do a little quick example here. we're going to have kind of the same case that we were thinking of in the previous example, where we've got a population of 5 with 3 successes. So we have 2 failures in the population. And now we're going to draw a sample of 4. Okay, so we've got those 5 total in the population, 3 successes, 2 failures. And we're going to pick a pretty big sample here. And if it's with replacement, if it's a binomial random variable, then every time we could pick any of these 5. So the number of successes, I, can be 0. Set notation here. I can be 0, it can be 1, 2, 3, or 4. No problem. Okay. But without replacement, you're not going to get a sample of 4 from this population that has 0 successes in it, because you'd have to have 4 fails, and you don't have 4 fails. And you're not actually going to get a sample of 4 that will even have 1 success, because you need 3 fails here. It's possible to get a sample of 4 that has 2 successes, or that has 3 successes. Okay, right? You could draw this sample would have 2, this sample would have 3, but you're also not going to get a sample that has 4 successes in it, because there aren't 4 successes in the population. Okay, so this inability to draw the same thing over and over again depresses the variance of the hypergeometric random variable relative to the binomial. Okay, so I'm teetering on talking about one last little point here, and that's this note about the values that I can take for the hypergeometric. So let's kind of zero in on that. I've kind of talked through the issue, but just maybe a little more systematically. So for all the discrete random variables in the table, I've got little notation here about the values that I can take here. And that would be called the support of the random variable. It's the values that it can take here. And it's complicated here for the hypergeometric random variable. So I want to unpack this very terse statement of the support for I that is in the set that is bounded by the maximum of 0 and small n minus capital N plus m, and bounded above by the minimum of n and m. That's not very intuitive, so let's take a look at it. What we're being told here is that the upper bound and the lower bound for the values that the random variable can take, write that here, values, random variable x, the support of random variable x are the values x can take. Okay, it's the things we could substitute in for that I and assign probabilities to them. And what this complicated statement is saying, written out in a little more detail here, is there's 4 possible cases. Okay, one is the case where the sample is small, the number of things we're sampling from the population, the sample is smaller than or equal to the total number of successes in the population, and it's also smaller than or equal to the total number of failures in the population. Right, that's size of the population minus the number of successes, that's the number of failures in the population. Okay, so we're in this case, we're not going to run out of failures or successes in the population. And so in this case, the support of the hypergeometric random variable is just the same as the binomial. It's possible to have 0 successes. It's possible to have all successes. Okay, so the danger of exhausting the sample is not something we have to worry about. But if we're in this situation, we're in the sample, the number of things we're taking out of the population is actually bigger than the total number of successes in the population, then that sample cannot have more successes than there actually are in the population. Okay, so in this case, we could still have 0 successes, but the upper bound on the random variable is the number of successes in the population. Okay. And similarly here, if the size of the sample is greater than the number of failures in the population, then the maximum number of failures is n minus m, capital N, minus small m. And that means that the minimum number of successes is n minus m plus n. Okay, let me make a note of that up here. This n minus, I'll write it a different way, n minus here. If we have all of the failures in the population, that's what n minus m is, and we subtract that from the size of our sample here, that is the minimum number of successes we can have. We've drawn every failure that's in the population. We've still got, n is bigger, so we've still got others to draw. That's the smallest. This is the minimum number of successes when n is greater than n minus m. Okay, so that's replacing our 0 here as our lower bound. Okay, and in this case, if the number of successes in the population is still bigger than our sample, then we could theoretically have the whole sample be successes. Okay, so that we could have, in a sample of n, we could have all successes and we wouldn't run out because we've still got some in the sample. And then in the case where both these things are true, we have to worry about running out of failures in the population and running out of successes, then our lower bound is n minus m plus 1, and our upper bound here is m. Okay. All right, and just thinking about that, in the example that we were working with for variance, okay, remember we had a population of 5, we drew a sample of 4, we had 3 successes in the population, and so that meant we had n minus m equals 2 failures in the population. And so what we're looking for here, I'm gonna copy this statement of the support, the maximum of 0 and small n minus m minus plus m all the way up to the minimum of n minus m. We're saying those are this is the range of values that x can take. Let's just plug in our numbers into the max and min. Okay. So the max of 0 and n minus capital M plus n equals the max of 0. N is 4, big N is 5, M is 3. It's the maximum of 0 and 2, that equals 2. Okay. And similarly, the minimum of N and M, that's a little bit easier to think about, but the minimum of the min of the sample size of 4 and the number of successes of the population 3 is 3, and so indeed I could be 2 or 3, just as we said there. Okay, so that's kind of in the weeds there. If you look real close at some of the previous videos, you might see that I had the wrong support initially in my table there. And it only occurred to me when I was talking about the variance or getting ready to talk about the variance in this lesson. So I fixed it here. And in a way, it's sort of a fitting way to tie up the hypergeometric random variable. It's something we kind of want to think about, the idea of sampling without replacement kind of seems to make sense. When you do sort of ad hoc sampling, you tend to not ask the same person twice or take the same marble twice, but the math of the hypergeometric random variable can get a lot more complicated because of the dependencies in it. So that's kind of a refrain from 200A. Whenever you relax in dependence assumptions, things can get kind of hairy. And I hope that at this point you're taking a nuanced perspective on it. This is certainly more complicated than we had with the binomial random variable, and going forward with sort of more theoretical things, we're going to be referencing the binomial random variable more often, but this didn't kill us either. It's not like we can't handle modeling out the dependency. Okay, so we've got one more discrete random variable in our table to look at, the Poisson random variable, and I'll see you in the next video to talk about that.